Hey everyone, welcome back to the channel Code with AKJ. Today is day 40 of solving LeetCode 75 challenge, and today's problem is binary tree right side view, which is from binary tree BFS section. So we are going to solve this problem in both BFS and DFS approaches along with its time and space complexity analysis. So if you're new here or enjoy such structured problem solving videos, don't forget to hit that subscribe button and hit that bell icon for the latest updates. So let's get started with our problem statement. So the problem statement says, given the root of a binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom. So given the root of a binary tree, we need to imagine we are standing on the right side of the tree and we need to return the values of the nodes we can see from top to bottom. So let's understand with these two examples. So in given example 1, we have given a binary tree, and suppose we are standing at this point, that is to the right side of this given binary tree, and we need to look at this particular binary tree, and the nodes which we are able to see need to be returned as an output. So the nodes which are visible here are 1, 3 and 4. So we'll return 1, 3 and 4 as an output. Coming to the example 2, if you are standing on the right side of this given tree, the nodes which you are able to see here are 1, 3, 4 and 5. So we'll return 1, 3, 4 and 5 as an answer. Coming to the example 3, the tree contains values 1, null and 3, which means it is a right skewed tree. So 1 has 3 as its right child. So the number of nodes which we are able to see from the right side of this given tree are 1 and 3. And coming to the example 4, the root is null, that is we need to return output as a null. So this could be an base case, that is if root is null we need to return null. So that is all about problem statement. So let's get started with our approach 1. So for our approach 1 we are going to use DFS. So we'll perform a modified pre-ordered traversal. So here we'll visit the right child before the left child. So the normal pre-ordered depth first search generally works by visiting root first and then left and then right. But in our modified pre-ordered DFS, we'll visit first right and then left. So in this approach, we'll maintain a level, and at the first node we visit at each level since it is the rightmost. So based on our modified pre-ordered DFS, since we are visiting right node first and we need the rightmost node of binary tree, since the question says we need the right view of a given binary tree. So that case would be handled if we consider visiting the nodes which are at the rightmost of the given binary tree. So that would be our approach. So let's quickly dry run with these two given examples, and then we'll move on to the time and space complexity, and later on we'll move on to the code. So according to the right side view of a given binary tree, so since we need to collect the rightmost node of the given binary tree at each level, that is for this given level we need 1, and for this given level we need 3, that is the rightmost node, and for the last level we need 4. So for each particular level we need the rightmost node. So that is why we need to visit the rightmost node first and then left. Since we need to collect the rightmost node at each level, our DFS approach works in this way. So at depth first traversal we'll go right first and then left. So at each new level we'll add the first node we see. Because we go first right will be the rightmost node at that level. So the condition where we need to store that particular value, that is we have reached a new level, would be this given condition, that is if depth value is equals to result vector size. That means we have visited this particular level for the first time and we'll store the node in our result vector and we'll move to the next level. So let's quickly understand this given condition by doing a quick dry run on this given example. So we'll first start a DFS call from root, sending the depth level and the result vector along with it as a parameter. So we'll start with the root node, that is 1. We'll compare the depth value and the result size. So initially the depth value is 0 and the result size is also 0. So since they both are equal, which means this is the first time we have visited this level, so we'll store the node which we have encountered first. So we'll store the value 1 in our result vector. So our result vector contains value 1. Now we'll give a right call to the root, that is root left, by increasing the depth value and by sending the result vector. So here the DFS call changes from root to 3 with depth value 1 and result vector. So now the depth value is 1, result size also 1. So which means we have visited this particular level for the first time. So the node which we are encountering first would be stored in our result vector. So here the node value is 3, so our result vector contains values 1 and 3. Again we'll give a write call. So now the depth value becomes 2, the current node value is 4, and we'll also send the result vector. We'll again compare the depth value, the value is 2 and the result size also 2. So again, which means we have visited this particular level for the first time, so the node which we are encountering would be stored in our result vector. So our result vector contains values 1, 3 and 4. So now it gives a write call. So since we have reached null, we'll get back to this previous node, and again this call gives a return call to this node, and this call gives a return calls to this node. Again, based on our modified pre-order DFS, now it will check for the left subtree. So 1 gives a left call to this node. So now the current node is 2, the depth value is 1, and we'll also send the result vector. Now the depth value is 1 and the result size is 3. So since they both doesn't match, it means we have already visited this level, so we'll skip this level. So 1 again gives a left call to its left value, so since it is null, it will give a return call, and again 2 gives a right call. So the current node is 5, the depth is 2, and we'll also send the result vector. So the depth here is 2 and the size of our result vector is 3. So since they both are not equal, which means we have already visited this level and we have already taken the firstmost node we have encountered at this level, so we'll also skip this part. So since we have completed all the recursive call for this given binary tree, we have found our values, that is 1, 3 and 4. So 1, 3 and 4 are the rightmost values at each particular level of this given binary tree, which is also our rightmost view of this given binary tree. So for this given binary tree, our answer would be 1, 3 and 4. So let's now do a try run on this given example. So again we'll compare both the depth value and the result vector size. So we'll start DFS call from the root, sending the depth value as 0 and the result value as initially empty, that is 0. So both the values matches, so this is the first level we have encountered, so we'll store the value which we have encountered first. So the result vector contains value 1. So we'll move to the right value first, so it will give a right call to its right node. So the depth value is 1, the result size is also 1, so this is the level which we have encountered first, so we'll store the node in our result vector. So our result vector contains values 1 and 3. So again 3 gives a right call, so since it is null, it will give a call back to its root node. So now 1 gives a left call. So the current node is 2, the depth is 1, and we also send a result vector. So depth here is 1 and the size of our result vector is 2. So since they both doesn't match, so it means we have already visited this particular level and we have already stored the rightmost node of this level. So it will give a left call again, increasing the depth. So the current node is 4, depth is 2, sending the result vector as a parameter. So we'll compare the depth and the result vector size. Here the depth is 2 and the result size here is also 2. So since they both match, it means we have visited this level for the first time. So now we'll store the node. So here the node we'll store here is 4. So the result vector contains values 1, 3 and 4. Again we'll give a left call. The current node is 5, increasing the depth by 1, that is 3, and sending the result vector as well for the call. So now let's compare the depth value and the result size. So the depth here is 3 and the result vector size is also 3, which means we have visited this particular level of this given binary tree for the first time. So the node which we have encountered will store this node in our result vector. So the result vector contains values 1, 3, 4 and 5. So it will again give a left call. So since we have reached null node, it will give a return call, and again it will give a return call, and in this way we will finish all the call from our recursive stack. And finally our answer for this given binary tree would be 1, 3, 4 and 5. So that is how our DFS approach works. So the time complexity of this approach would be O of n, as we are visiting each and every node once, and whereas the space complexity here would be O of height of the binary tree, and for the recursive stack O of height. So the overall space complexity would be O of height of a binary tree. So let's quickly code this approach and let's submit. So here's the code for our brute force approach we have discussed and did a quick dry run on these two examples. So here I have taken the vector of int of result, which will store the right side view of our given binary tree. Also sending the depth value, which would be initially 0. So this DFS function would calculate all the right side view values and store it in our result variable. And finally we'll return that result vector. So our DFS function works like this. So it takes node, the depth value, that is the level, and the result vector as an input. So the base case here would be that if node is null, we'll return from there. And the condition where we decide that we have visited this particular level for the first time is if level is equals to the result vector size, then we have visited that particular level for the first time. And since we are visiting the rightmost node of that particular level, we'll get our right side view of our binary tree. So we'll store that particular node value in our result vector, and we'll give a right call first by increasing the level, and then we'll give a left call. So in this way our DFS function works. With the help of modified preordered, we are able to store the right side view of our binary tree. So let's quickly run this code. It's working. So let's submit. As you can see, it gives a successful submission. Here the time complexity would be O of n, as we are visiting each and every node once, and space complexity here would be height of tree, that is stack space, and in the worst case it would be O of n. That is for a case if the given binary tree is a skew tree. So now let's talk about the BFS approach, which is generally the preferred one since it is considered under the BFS section of our LeetCode 75 challenge. This approach will use a queue and process the nodes level by level. Since this process goes level by level, we'll store the last node of each level in the result vector. So it's pretty simple. Here we'll use a queue. So since BFS approach goes level by level, we'll store all the values at each level in a queue, and we'll grab the lastmost node at each level. That is, for this given level the values would be 1, and at this given level the node values are 2 and 3, and at this given level the node values are 5 and 4. So at each level we'll grab the lastmost node. That is, for this level the value would be 1, and for this level the lastmost node is 3, and for the final level the lastmost node here is 4. So after grabbing all these values, we'll store in our result vector. So for this given example, the first level contains node value 1, the second level contains node values 2 and 3, the third level contains values 4, and the final level contains the value 5. And for each level we'll take the lastmost node. So for this level the lastmost node is 1, and for this second level the lastmost node is 3, and for the third level the value is 4, and the fourth level the value is 5. So in this way we'll store all this value in our result vector and we'll return this given vector. So this approach is pretty much easy and efficient, and since we are using a queue, the space complexity varies based on the different shape of our given binary tree. So let's do a quick dry run of how our BFS approach works. So the first step in our BFS approach would be to take a queue of type tree node, and we'll initially push our root node. So for this given example, the initial value, that is the root node, would be 1. So we'll run a loop until or unless this queue becomes empty. So the steps inside our loop would be first to check the size of our queue. So here the size is 1, and we'll run a loop for the given size, and we'll check if we have reached the last node or not using the for loop. The first step here would be to pop this current node, that is we'll store in variable node the current value, that is using queue.front, and we'll also pop this current node from the queue using queue.pop. And after grabbing this current node, we'll check whether this current node is the rightmost node or not using a for loop. So if it is a rightmost node, then we'll store in our result vector, and after storing it we'll try to push its left child and right child. So the left child of this given node is 2 and the right child of this given node is 3. So now the queue contains values 2 and 3. So again we'll check the size of our queue. So here the size is 2. Now we'll use a for loop to find the lastmost node, and we'll try to pop the current node using queue.front and queue.pop, and we'll check whether the current node is a last node or not. If it is not, then we'll simply queue.pop, and if it is a last node, we'll store that in our result vector. And while popping, we'll store its left child and right child. So the current node here is 2, and we'll store the left child and right child of this current node into our queue. So the left child is null, right child is 5. So the queue contains 3 and 5 here. And since 2 is not the lastmost node, we will pop this and we'll again move to the next node. So here the current node is 3. So since 3 is the lastmost node of this current levels 2, we'll store this 3 value in our result vector and we'll push its left child and right child. So now currently the queue contains values 5 and 4. And again we'll use these operations by finding the size, and then again we'll use a for loop for this particular size, and we'll check if the current node is the last node or not. If it is not, then we'll simply pop it and move to the next node, and if it is a last node, we'll store it in our result vector and send its left child and right child inside our queue. So since the left child and right child of 5 and 4 are null, so the queue becomes empty and we'll stop our while loop. In this way our BFS approach works. With the help of a queue data structure, we'll store the nodes at each level and we'll find the rightmost node of each and every level and store it in our result vector. So the time complexity of this approach would be O of n, as we are visiting each and every node once, and the space complexity of this approach would be O of n as well for the queue in the worst case. We'll try to discuss the time and space complexity analysis in detail for each and every binary tree. That is, for different scenarios of binary tree, the time and space complexity varies. So we'll discuss that part in the time and space complexity analysis. So let's quickly code this approach and let's submit. So here's the code for our BFS approach, where we are using queue data structure to store all the values at each level and finding the lastmost node at each level, which would be our right side view of a given binary tree. So the base case here would be, according to our example 4, that is, if root is null, we'll return the result vector, that is an empty vector. We'll take the help of queue, that is of tree node star type. So initially we'll push the root value inside our queue and we'll run a while loop until or unless the queue becomes empty. We'll first grab the size of our queue and we'll use a for loop to find the lastmost node, that is the rightmost node of the particular level. We'll first grab the node value with the help of queue.front and queue.pop, and we'll check if the current node is the rightmost node or not with the help of this given condition, that is, if I is equals to the level size -1, which means we have found the rightmost node. So we'll store that node in our result vector. And finally, after storing the rightmost node in our result vector, push node left value and node right value into our queue. So in this way our process works until or unless queue becomes empty, and if queue becomes empty, we have found all our right side nodes if we are standing at the right side of this given binary tree. And finally we'll return our result variable. So let's quickly run this code. Okay, it's working. So let's submit. As you can see, this approach also gives us successful submission where we have used BFS. So let's analyze the time and space complexity for both the approaches we have discussed in this given problem statement in different scenarios of a given binary tree. So in DFS we explore downward through recursive calls, and at any given point we hold one path from root to a leaf. So the number of function calls in the call stack at once is equals to the height of the tree height. So DFS uses space proportional to the maximum depth of a given binary tree due to recursion. So therefore the space complexity of our DFS approach would be O of h for a general tree. Whereas if we consider the tree is a skew tree, then the height would be O of n and the recursive call space will also be O of n. Whereas if we consider the balanced tree, the height would be O of log n and recursive call space would also be O of log n. And coming to the BFS approach, since we are storing each and every node at each level, space complexity of our BFS approach would be O of width of a binary tree. If we consider a general tree, that is O of width for a maximum width of a given tree, and the space would also be O of width. And coming to the skew tree, since it can be a left skew tree or right skew tree, for each level we'll only have one node, so the maximum width would be O of 1. So the overall space complexity for our BFS approach would also be O of 1. And for a balanced tree, the maximum width would be O of n by 2, that is, if we consider the last level of a given binary tree would contain the number of nodes divided by 2. So the overall space complexity of our BFS approach would be O of n. So this would be the space complexity of both the approaches if we consider different scenarios, whereas the time complexity remains same, that is O of n, as we are visiting each and every node only once. That's it for day 39. We have covered a clean BFS approach with queue and a DFS method with recursion. and time and space complexity trade-offs. So which one do you prefer? Comment below. If you found this video helpful, like, subscribe and comment, and share it with your friends who are doing the LeetCode 75 challenge. Thanks for watching, and I'll see you in the next one.